going to talk today about the end of the universe. This is a subject that's dear to my heart. It's not my main area of research, but it's something that I've thought about and worked on here and there throughout my career. I'll talk to you about a few different possibilities for that. But whenever I talk about a big, heavy subject like this, I like to start things off with a little bit of poetry. So, some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. This is the famous poem by Robert Frost from 1920. That was a long time ago. Of course, now we know the answer. It's fire. The world will end in fire. In something like 1 billion years, the sun will expand and brighten enough to boil off the oceans of the Earth and leave the Earth just a dry, lifeless, empty clump of molten rock. So that's the Earth. We know how that's going to go. But as a cosmologist, I'm interested in a bigger question. I'm interested in what will happen to the entire universe. How will that eventually end? What is going to happen to everything everywhere? So today I'll go through a few possibilities. I'll talk about the Big Crunch, the heat death, the Big Rip, and my personal favorite, vacuum decay. But before I get to that, I'll start with just kind of making sure we're all on the same page where we are in this cosmos. So this is a picture of the Milky Way galaxy, the galaxy in which we live. This is from the perspective of the southern hemisphere, where you get kind of a better view of the center of the Milky Way. So that bulge in the center there, it's not very easy to see with this pointer, but that's the middle of the Milky Way. If we were outside the galaxy, it would look kind of like this. This is actually our nearest neighbor, large galaxy, the Andromeda galaxy, but it's very similar in form to the Milky Way. There's a disk with spiral arms. There's a clump in the center with a lot of stars and gas and dust and a supermassive black hole, and we're somewhere out on the outskirts. Now, galaxies like this are all over the universe. With space telescopes like JWST or the Hubble Space Telescope, we can see far, far into the distant reaches of the cosmos, and we can get amazing images like this one, where in this image, every one of those little splotches is a galaxy. There are actually a couple of places here where there are individual stars. The things with points on them are generally stars. They have those points because the light is so bright that it interacts with parts of the telescope. But every little colorful smudge there is a galaxy, a collection of millions or billions of stars in a galaxy somehow like our own. And by looking at images like this, we can learn a lot about the history of the universe and ultimately about the future. But the reason we can learn about the history is that when we look at galaxies, distant galaxies like this, we're really looking into the past, because every time we look at something far away, the light has taken some amount of time to get to us from that point. So the farther away we're looking, the farther into the past we're looking. And this is not just about galaxies, by the way. This is everyday life. Every time you look at anything, you're looking into the past, because light takes time to travel. So if I look at the front row, I'm looking at maybe 15 feet away, something like that. And light takes about a nanosecond to travel a foot. And so I'm looking at about 15 nanoseconds ago, if I'm looking at the front row. If I'm looking at the very back of the auditorium, that's hundreds of nanoseconds in the past. So you're all in the past, according to me. And every time we look into the cosmos, we're looking deeper and deeper into the past. And the galaxies in this image are billions of years in the past, according to us. The light took so long to get to us that we're looking at billions and billions of years, maybe 10 billion, in some cases, maybe 13 billion years in the past. The universe is about 13.8 billion years old. And so these galaxies are some of the oldest images the light has taken the longest time to get to us. So that's one thing that we learn looking at images like this. We also learn that all of the other galaxies, all the distant galaxies, are moving away from us. And we can see that because the light that they emit is stretched out. As the universe is expanding, the galaxies are getting farther away from us and their light gets stretched out to longer wavelengths. And so that's why this image was taken with an infrared telescope, because although the light was emitted in visible light or ultraviolet light, or sometimes X-rays, that light has been stretched out by the expansion of the universe. And so all of these galaxies are now seen to us in infrared light. The light has been stretched out that much. So I mentioned the universe is expanding. The way the universe is expanding is just that there's more space in between galaxies. So I made a very sophisticated animation of this. Okay, so the galaxies themselves are not getting bigger, but there's more space in between galaxies as the universe is expanding. There's just more empty space going on. And when we look at the expansion of the universe and we see that things are getting farther apart all the time, we can learn something about the early times of the universe, because we can just say, well, if things are getting farther away now, then they must have been closer together in the past. And that's really the whole idea of the Big Bang theory. The Big Bang theory says that since the universe is expanding now and things are getting farther apart and the universe is getting cooler as all the energy is being dissipated and spread out to larger spaces, that means that in the past everything must have been closer together and everything must have been hotter and denser because it was all much closer together, because the universe was in some sense smaller than it is today. And so you can take these two things that I just told you. One, that when we look into the universe, we're looking into the past. And two, that the universe was hotter and denser in the past. And you can ask, well, does that mean that as we look farther away, we see a universe that was hotter and denser? And the answer is, yeah, we do. And you could also ask, could you see so far back that you're looking at the universe when it was so hot and dense that the whole universe was just plasma, just hot, dense plasma of the Big Bang? And the answer to that is also yes. We can see the end stages of the Big Bang. We can see the time when the universe was so hot and dense that it was glowing, that it was just roiling with heat. So there's a sort of illustration of this here where we're in the modern universe, 13.8 billion years after the beginning, and as we look farther into the distance, we're seeing farther into the past. So that purple band, that's the Hubble Ultra Deep Field. That's one of the most distant pictures we had before JWST was launched from the Hubble Space Telescope. That was looking at galaxies that were during about the first 500 million years of the universe. With JWST, we can actually see a little bit farther than that, to maybe 200 million years after the beginning in some cases. But if you look farther than that, if you look beyond all the galaxies, we get to the point where we're looking at what's called the radiation era. It's also known as the hot Big Bang, the time when the universe really was just hot and dense and glowing with heat. And this is drawn as a kind of shell around us, because if you think about it, in every direction you look, if you look far enough away, you're looking so far into the past that you're looking toward the beginning of the universe. So the beginning of the universe is in every direction. Right? The Big Bang is in every direction. It's not a specific point. It's everywhere if you look far enough away. So you can ask, what does that look like? I just told you we can see it, right? So what does it look like? Well, if you take the whole sky and you look at it with visible light, you see something like this. So this is, you take the whole sky, you stretch it out to, make it an oval, to, everything around you. And you can see the galaxy stretched across the sky. You can see the large and small Magellanic Clouds, which are the little satellite galaxies of the Milky Way. So that's what the sky looks like with visible light. But I told you before that as the universe expands, the light from distant things gets stretched out. Now the light from the early galaxies gets stretched out to infrared radiation, but the light from the Big Bang gets stretched out to microwave radiation. So like sort of around radio wave frequencies. And if you make a picture like this of the universe with just microwave light, it actually looks very different. It looks kind of like this. Okay, it's not the most interesting picture. I'll show you. I'll show you some more detail. We'll stretch out the contrast, but the point is that it kind of looks the same in every direction. It's sort of the same temperature in every direction, the radiation coming from the Big Bang. It's very uniform, it's very bright, it's a very just light coming from everywhere that looks basically the same, which makes sense because if you look in every direction and you're seeing the Big Bang in every direction, then the Big Bang was kind of the same in every direction. There's some subtleties to that you get into when you study cosmology, but that's essentially what we see. And the reason that we know that this is actually from the hot early universe and not just some spread out kind of weird stars is that we can take the spectrum of this light. So when you take a spectrum of something, you're stretching out the light into, like putting it through a prism. If you put white light through a prism, you see the rainbow. You can do that same thing with microwave light, and you can see how much light there is at different colors in the microwave part of the spectrum. So this is a spectrum of this background light, the cosmic microwave background light, where what we've done here is we've plotted the intensity of the light at different colors of microwave light. So, you know, the bulk of the light comes in at this color that I've called purple, which is some color of microwave light. And then there's a little less at a redder side of that, a little less at the bluer side of that. So we're looking at how much light is at different parts of that spectrum. And the weird thing about this is so those little squares, those are the data, right? Those are the data points. That's how much light we see at every part of that spectrum. The line is the theoretical line that you'd get if you just plotted what the spectrum looks like of something that's glowing because it's hot. It's called black body radiation. So if you just take like a poker and you stick it in the fire and it heats up and it glows orange like that, and you take the spectrum of that light, it makes that same shape, that same curve, the black body curve. So what this graph is telling us is that when we look at that picture of the microwave light from everywhere in the sky, what we're seeing is something that's glowing because it's hot. It's exactly the same kind of radiation that you get from something that's just glowing because it's hot. And that tells us that everywhere in the universe, if you look far enough away, you're looking at part of space at a time when all of space was glowing with its own heat, with this plasma of the very early universe. Now, this first measurement of this was made in the 1960s, and shortly thereafter, astronomers put satellites up into the sky to get better pictures of the cosmic microwave background. This was one of the first ones where basically they just take that light and they stretch out the contrast a lot. So here, the difference between the red and the blue in this picture is 1 part in 100,000, just a little tiny variation. But there is some variation, and we've got better pictures since then. This is from the early 2000s, where we've got more and more contrast, so we're able to see more detail, where we're really looking at that earliest light in the universe. And then this is the most recent picture from a satellite called Planck, showing all those little spots. And those spots are places where that plasma in the early universe was a little bit hotter or a little bit cooler, a little bit more dense or a little bit less dense. So there was a little bit of variation in that early universe plasma. There was actually sound waves moving through it. It was so dense that it was loud. And those sound waves are bouncing around and creating these little ripples in the plasma of the very early universe. And as astronomers, this is one of our favorite pictures of the universe because this is something that carries just a huge amount of information. It tells us a lot about the conditions of the very early universe, but it also gives us a lot of information about everything between here and there. So everything else in the universe affects how that light passes to us from the very distant reaches, and so we can learn a lot about what the universe is made of. By looking at those little ripples, we can learn about how the early universe, like what it was made of at the time because of how the sound waves were moving through it. And that gives us information about the structure of the cosmos, and ultimately it can give us some information about the future of the cosmos because it tells us something about what the universe is made of and how it's been evolving over time. And so that brings us to our first end of the universe scenario, the Big Crunch. So the Big Crunch is an idea that's been around for a long time. In the 1960s, it was kind of the favored idea for the end of the universe, and so it's probably one that you've heard of before. The idea behind the Big Crunch is fairly simple. So we see that the universe is expanding. We see that galaxies are getting farther away from each other. But we also know that galaxies have gravity, right? And they've got to be attracting each other at some level. And so there's this question, and there's been this question since this observation of the expansion of the universe was first made, like, is the expansion going to carry on forever, or is it going to turn around? Is the gravity going to win and pull everything back? And for a long time, we didn't know the answer to that question. We had some ideas that maybe the gravity would win and everything would come back. And this would lead to everything getting closer together instead of farther apart. And things start to get a little bit crowded. And in the scenario of the Big Crunch, several things happen as this crowding comes together. One thing that happens that you can kind of see just by looking at this picture is that some of those galaxies are going to start crashing into each other, right? And we actually see collisions of galaxies in the universe all the time, even now, and we're not in a Big Crunch now, but we do see sometimes that galaxies collide with each other. Just because galaxies sometimes form close together, and so they're already in each other's gravitational pull, and sometimes they merge. This is an image of a galaxy merger. This one is called the mice because there's tails coming off of it. Those are called tidal tails. What happens is that the galaxies come together and gravity is stretching and pulling and merging things, and sometimes stars get flung off in the chaos in these long streamers called tidal tails. And there are entire catalogs of merging galaxies. Cosmic train wrecks is what we often call them in astronomy. And in these pictures, you can see that these are kind of colorful, right? So what happens is, as the galaxies crash together, the stars get kind of moved around and you get these long streams, but also all of the gas in the galaxies crashes together, and when that gas crashes together, that forms bursts of new stars. So that gas comes together, that's the fuel for new stars to be forming, and so you get parts of these images, you can see little bits of red and blue that are new stars that just formed, and then they're going to go supernova, and you can get bits of sort of dust moving around in these merger galaxies because of the supernovae. A bunch of other things happen. You get star formation, you get the black holes in the centers of the galaxies come together and spiral in and collide with each other. Sometimes it creates jets of radiation that go out of the galaxies. It's a big, colorful, chaotic event. And, fortunately, we're going to get a good view of that in about 4 billion years because the Andromeda galaxy that I showed you earlier is coming for us. So the Andromeda galaxy is our nearest neighbor large galaxy, and Andromeda and us, we were born close together, so close together that we are already in each other's gravitational pull. And the Andromeda galaxy is currently coming toward us at about 110 kilometers per second. Fortunately, it's very far away at the moment, so it's going to take a while to get here. It's going to take about 4 billion years, but that is probably going to happen. That collision will happen, and when that happens, we'll get to see that cosmic train wreck up close. Now, I mentioned the Earth will be dead. Okay, don't worry about that. The Earth will already be dead in 4 billion years. we only have life on this planet for maybe 1 billion years, right? Because that's when the sun boils off the oceans. We're gone. In 4 billion years, it might even be that like the sun has expanded so much that the Earth might have already fallen in. Okay, so we're really gone. Okay, but one could wonder, like, what if we managed to leave, like a little webcam in orbit around something to take pictures? What would it look like? Right? We kind of want to know what it would look like. And fortunately, astronomers at NASA and other places have made some simulations of what this would look like. So this is an image, simulated image of the Milky Way galaxy, kind of stretching across the sky. And there's you can kind of see that little smudge a little bit to the left of it. That's the Andromeda galaxy as it's seen today. Let's fast forward 2 billion years. Okay, it's coming. It's getting closer. 3.75 billion years. It's much closer now, and oh no, things are starting to happen. You can see those red and blue clusters of new star formation. You can start to see some of that dusty stuff where the supernovae have already been going off. It just gets worse, and then at some point, like, there's the collision, and then it kind of like rebounds a little bit, so it kind of starts to stretch out. You can see those tidal tails forming as the stars get moved around, and then it comes back in again, and everything gets kind of clumped up, and after a while, in about 7 billion years, it's just a sort of elliptical blob of stars, mostly dead stars at that point. But if the solar system at some level is still there, this will not necessarily kill it, because even when galaxies collide with each other, the chance of any two stars hitting each other is very low. There's a lot of space between stars, even in a galaxy, even when those galaxies are colliding with each other. And so most of the stars are just going to miss, like birds in the sky just passing by each other. So this is not, so even in a big crunch scenario, when all of the galaxies are colliding with each other, this is not what kills the stars, okay? There's something else that kills the stars in the Big Crunch, and that's really the fact that there are stars at all. So when space is getting smaller, the matter is getting more compressed in the sense that the galaxies are coming closer together, but also the radiation is getting more compressed because there's less space for all that radiation to flow around in. And, and it's not just that the radiation is getting more compressed, it's also going to higher frequencies. It's becoming harder radiation, because I said before, as the universe expands, it stretches out light. If it's collapsing, it's compressing light. And so light that was, harmlessly in the microwave part of the spectrum shifts to the infrared, and shifts to visible light, and then shifts to ultraviolet light, and then X-ray light, and then gamma radiation. And that gets really uncomfortable. And so because all of these stars have been shining all this time and putting out visible light and ultraviolet light and X-rays, and there's gamma ray bursts, and there's all this radiation out there in the universe, when the universe starts to collapse, all that hard radiation fills space. And instead of space being dark and empty, space becomes full of hard radiation. And an astronomer named Martin Rees in the UK calculated at some point in the late 1960s, when we thought that the Big Crunch was coming, he went ahead and calculated exactly how this process works. And he worked out that as the Big Crunch is approaching, space gets so full of hard radiation that it starts to ignite the surfaces of stars, and the surfaces of stars start having thermonuclear explosions all around them. And that's not survivable. So once the stars are catching fire with thermonuclear explosions, that's it. That's it. You don't get out of that. So that's the Big Crunch. Fortunately, that seems very unlikely. The most likely end of the universe, as far as we can tell, is something called the heat death. The heat death is also sometimes called the Big Freeze, and I'll explain why. I mentioned the universe is expanding. I mentioned that the galaxies are getting farther apart, but they're also pulling on each other, right? They're trying to slow down that expansion because they're pulling on each other. In the late 1990s, astronomers were trying to figure out if the universe would collapse again in a big crunch, or if the universe would continue expanding forever. This question of, is the expansion more important, or is the gravity of everything more important? And so astronomers went ahead and they started measuring the rate of expansion. Specifically, they started measuring how quickly the expansion was slowing down. A parameter called the deceleration parameter. And they fully expected that they were going to be able to measure that number, because really the physics here is very much like if you take a ball and you throw it up into the air. Okay, what's happening is that, like, imagine that when I push on the ball, that's the Big Bang. That's what starts off the expansion, okay? And the ball moves upward, but it's still pulling on the Earth. The Earth is still pulling on that. Gravity is always there, slowing it down. So when I throw a ball into the air, it goes up for a bit, it slows down, and slows down. Eventually it'll stop and it'll fall back because the gravity will win. If I could throw it much faster, then I'm not that strong, but if I could throw it at 11.2 kilometers a second, which would be a bit more than I can manage, then it would be going so fast that the energy it had would be enough to overcome the gravitational pull of the Earth, and it would never come back. It would always be slowing down because it would still feel the pull of the Earth, and that's a sort of infinite force. You're always gonna feel the gravity as you go farther away, but it would always be slowing down. If I send it at exactly 11.2 kilometers a second, it'll slow down and it'll reach zero at infinite distance. Okay, so it'll just keep going forever and it'll always be slowing down a little bit. If I threw it a lot faster than that, then it would kind of coast, but it would always be, it would be slowing down at least for a while, right? And so astronomers were figuring, like, those are the possibilities, right? So something up, it either comes back or it doesn't, but whatever happens, gravity is pulling it, it slows down. So they went ahead and they measured the deceleration parameter, and they got a negative number. It turns out the universe was not slowing down at all, the expansion was speeding up. And this was exactly as weird as if you throw the ball up into the air, and instead of slowing down and falling again, it slows down for a little while and then shoots off into space. Very similar physics, really, because if you imagine that's happening, you figure there has to be something else there making the ball shoot off into space. Because if it's just gravity, if it's just that initial push, the Big Bang, and gravity, it has to slow down. There's no other option. But, maybe you threw it up into the air and there was a big wind, or maybe it had rockets at the bottom of it and it shot off into space that way. Somehow, something interfered and made the universe expand faster. And we still don't know what it was that did that. We think maybe there's just a property of the universe where that's a thing that happens. Whatever is making the universe expand faster, we call it dark energy. That's just a filler term we use for the thing that's making the universe expand faster. But our best guess is that it's something called the cosmological constant, where every bit of space just has a little bit of stretchiness built in, basically. And when you get into a situation where you have a whole lot of space and not a whole lot of stuff, then that stretchiness kind of takes over, it overcomes the gravity. And so instead of things slowing down because gravity is pulling on them, there's so much stretchiness in space that it starts speeding things up and moving them away. That's a cosmological constant. That's an idea that goes back as far as Einstein, and maybe that's what's happening. If that's the case, if that's what dark energy is, then we know what's going to happen next. The universe is going to continue to expand and accelerate in its expansion. Galaxies are going to get farther and farther away from us, not the ones that are already next to us, like Andromeda, that one's going to merge with us, but the distant ones are going to get farther and farther away from us and harder to see, because their light will be stretched out so much because they'll be moving away from us so quickly that we won't be able to see them anymore. In about 100 billion years, our galaxy, whatever's left of it after the merger with Andromeda and the little galaxies nearby, our galaxy will be alone in the universe. In 100 billion years, we will not be able to see other galaxies. You could take the Hubble Space Telescope or JWST, you could put them up and stare out into the night sky as long as you want, and you would not see anything at all. In 100 billion years, most of the stars in our own galaxy will have faded away. There will be a few red dwarfs still shining. We will not be able to see other galaxies. We won't be able to see the cosmic microwave background either. It will also have been stretched out so much that we won't be able to see it. A little while after that, the rest of the stars in our galaxy will burn out. There will be some black holes in the galaxy, and those will evaporate away. Eventually, particles will decay, and the universe will be left cold, dark, empty, and with nothing happening. That's the heat death. It's kind of a sad story. The reason it's called the heat death, by the way, is that as this process occurs, as everything is decaying, what's really happening is it's decaying into like waste heat. There's this idea in physics called the second law of thermodynamics, which is this idea that in the future, disorder always increases. So, in fact, you can tell which direction the future is by the direction where disorder is increasing, where if you have a machine running, it's going to slowly break down. The friction is going to ruin your wheels, and everything will kind of decay into entropy, right? And we think that happens to the universe. The universe will decay into entropy, into heat, into this waste heat. And at some point, we'll get to the maximum entropy state where everything will have decayed so much that it can't decay anymore, that everything is fully disordered. And to the extent where the entropy is so maximized, it can't get any higher, which means that there's kind of no future anymore because there's no direction in which disorder increases. And that's why it's called the heat death, because it's this death of the universe sort of through the waste heat of everything. And at that point, it's kind of the case that nothing important can happen anymore because there's no future, there's no way for new order to appear. So yeah, it's not a fun story. It could be worse. It could be worse. There is a possibility, it's a remote one, but there is a possibility that dark energy is something other than a cosmological constant that could wreak more havoc on the universe than a cosmological constant does. Now let me go back and explain a little bit more about the cosmological constant. So the cosmological constant was an idea invented by Einstein because he saw a problem with the universe. When Einstein was working this out, he knew about stars, but he didn't know about other galaxies because we actually couldn't see other galaxies well enough to know that they were out there. And so at that time, people thought that it was kind of just, the universe was just a bunch of stars that were kind of separated. Now we know it's more about galaxies. So I'm going to talk about this in terms of galaxies, but it's the same argument with stars. So the idea is there's a whole lot of galaxies in the universe, and they're all pulling on each other. If the universe is unchanging forever, which is how people thought about the universe when Einstein was first writing this stuff down, if the universe is totally unchanging, just static, then it's weird that all those other galaxies are out there because the gravity should have pulled them all together a long time ago. Right? How are they just stuck there in the sky? If the universe is unchanging, the gravity should have pulled them together. Einstein knew a lot about gravity. He thought this must have happened. And so he figured there had to be something in the equations to prevent this, some kind of extra thing in the universe that would stop this happening. And so he invented a force that would kind of push against the galaxies, that would kind of stop the collapse by kind of bracing everything against everything else. So the gravity is kind of pulling in, but this cosmological constant, whatever it is, would be kind of pushing out, exactly balancing everything to keep that collapse from happening. So the idea was, the universe obviously hasn't collapsed, and the only explanation for that, if it's a fully static universe, is something's holding it up. That something was a cosmological constant. when it was discovered that the universe is actually expanding, there was a different explanation for why the universe hadn't collapsed. It's because it was already moving away. He threw away the cosmological constant. He said, sorry, my bad, not a good idea. Took it out of the equations, and we carried on. But now we do need something that pushes against the galaxies. We need something to make the universe expand faster. And so we're thinking maybe we should put the cosmological constant back in. If the universe does have a cosmological constant in it, then all the cosmological constant does is it just kind of moves the galaxies away from each other. But as the universe gets bigger, because the cosmological constant is like a property of space, when there's more space, there's more cosmological constant. So it kind of turns out that cosmological constant will just take over the universe eventually. And I'll show you with a graph how that happens. So if we look at the density of stuff as a function of time, so density being sort of energy per unit volume as a function of time. For matter, as the universe is expanding, there's less matter in the same amount of space. Because the universe is getting bigger, the matter is getting stretched out, or spread out. And so the density of matter goes down over time. The density of radiation also goes down over time. It actually goes down faster because as the radiation is spreading out, it's also getting stretched out, and so it goes to lower energies. So it gives you another factor of decreasing for the density, for the energy density of radiation. So matter and radiation are both getting more diffuse in the universe as the universe expands. But a cosmological constant is a property of space itself. So as there's more space, there's just the same density of cosmological constant, because you have twice as much space, now you have twice as much cosmological constant, the density is the same. It's always the same amount per cubic meter or whatever. But what that means is that as you go into the future, the cosmological constant becomes more and more of what the universe is. And so over time, the matter and the radiation kind of fade away because they become less and less important. And really all that's left is a cosmological constant. And that's when you end up with something like a heat death, where everything else kind of fades away, becomes really unimportant. But the thing the cosmological constant doesn't do is it doesn't actually break anything, because it's just moving stuff away from everything else. It's not actually like pulling things apart. In a universe with a cosmological constant, our galaxy gets moved away from another galaxy, but neither galaxy gets like ripped apart itself. Because if you think about it, like there's a certain amount of space that our galaxy lives in. There's a certain amount of cosmological constant in that space. And the amount of cosmological constant in that space doesn't get bigger, right? If you kind of draw a sphere around the galaxy, if it's there now, it's going to be there in the future because the cosmological constant doesn't build up. But there are possibilities, or there's sort of theoretical ideas for dark energy where the amount of dark energy would increase over time. And you could get something where you get more and more dark energy in the same space. It's called phantom dark energy. And what would happen there is that in that little sphere we've drawn around our galaxy, instead of just being sort of stable and moving away from everything else, the dark energy will build up inside that little sphere and start pulling at the galaxy, pulling at the stars, pulling at all of the stuff within the galaxy. And it gets even worse than that, because as it builds up, it builds up in the galaxy, but it also builds up in the solar system, and it builds up in the planet, it builds up in this room, and the dark energy kind of comes from within and kind of pulls everything apart. And you can do calculations where you find that in some finite amount of time, based on what kind of phantom dark energy you have, in some amount of time, it would eventually pull apart the entire universe. Now, this is kind of a bit of an outlandish theory, right? It's something that most astronomers, most physicists don't think is very likely, but it's mainstream enough that NASA put out an animation of it many years ago. I'm going to show you this animation. It's very low resolution. It's from like the 1990s or something. I don't know, but I love it because I just love that they did this. Okay, so what we're going to see is we're going to see some expansion, and then we're going to see where the dark energy starts to go bad. Okay, here we go. Okay, wait, I gotta show that again. Okay, so you have expansion, expansion, expansion. Oh no. Okay, so that final pulling apart thing, that's the big rip. That's where everything gets destroyed. And it really goes from kind of the bigger scales to the smaller scales. Now, we think it's probably not going to happen for various theoretical reasons, but the only way we can really know if it's going to happen, or the only way we have to sort of test this idea, is to measure something something about the cosmos that we call the equation of state parameter. I'm going to show you 3 equations, the only equations. I'm sorry, got to do these. Okay, so there's this number we call W. It's the equation of state parameter. It's defined as the pressure divided by the density for whatever the universe is made of. Okay, and you can define that for different kinds of things as well, but we're talking about basically the whole universe, or really just dark energy, but dark energy is most of the universe, so you can ignore everything else. Okay. If the dark energy is a cosmological constant, then this W is exactly equal to -1. I won't get into how weird it is to have something where the pressure and the density have opposite signs. It's a whole thing. It's why accelerated expansion can happen, but for a cosmological constant, that's an exact equation. The W is equal to -1. And we can go and we can measure W and see how close it is to -1 or what the number is, right? If W is anything less than -1, then you have phantom dark energy. So if it's -1.5, if it's -2, whatever, that's phantom dark energy. That's when you get a big rip. And you can calculate based on what W is exactly when the big rip will happen. Okay, and we have ways to measure W. We have the Planck satellite. That's the one that gave us that really high resolution picture of the cosmic microwave background. And the Planck satellite takes, measures what the universe is made of, tries to figure out this balance between the pressure and the density. And the Planck satellite took a measurement of this, and it got W equals -1.028 plus or minus 0.032. Now, you might notice -1.028 is less than -1. But there's also that error bar, right, that 0.032. That means that the real number could be 1.028 plus 0.032, or it could be -1.028 minus 0.032. If it's the first one, that's good. W is not less than -1, awesome. If it's the second one, that's not so great, right? And we just don't have the precision right now to say where W is exactly within those parameters. But what we can do is we can take the worst case scenario, the idea that maybe W is -1.028 minus 0.032, the lowest it could be within the parameters of our measurement. We can take that worst case scenario, and we can figure out, if that's the case, how long is it going to be till we have this terrible big rip? And we can get a number. Okay, so what we can say is that we have at least 188 billion years based on this measurement. And I already told you that after 100 billion years, the universe is uninteresting anyway. So, whatever. We won't even be able to see galaxies anymore. What's the point of existence? You can just give up on the universe if it's going to take that long. Okay, but probably it's not going to happen. But if it does, we have this long, which means that we can do some more calculations. And as a cosmologist, it's always fun to do calculations about the end of the universe. So there was the paper that first proposed this kind of scenario. It was called, the paper was called something like a phantom menace, W minus less than -1 creates a cosmic doomsday. It was an excellent paper. Anyway, this paper created like a little timetable of doom about when different bad things happen based on a particular calculation of W. So I went ahead and I updated that for the scenario that fits the data now. Okay, so the Big Rip would happen in 188 billion years or longer, based on our current measurements, right? So 2 billion years before the Big Rip, galaxy clusters get pulled apart, so the galaxies get pulled out of galaxy clusters. 140 million years before the Big Rip, the Milky Way is destroyed. 7 months before the Big Rip, the solar system is unbound, meaning the planets get pulled away from us. Just an hour before the ultimate Big Rip, the Earth explodes. And a tiny fraction of a second before the Big Rip, atoms are pulled apart and destroyed. So you can calculate all this, just a very simple equation. It's a lot of fun. As I said, fortunately, we think it's probably not going to happen, the Big Rip. There's a few reasons. One of them is that the data kind of point more toward a cosmological constant. Another is that there are certain theoretical sort of reasons why we think maybe it's not the best theory, things to do with like conserving energy in certain ways. But if it were going to happen, we know at least we have about 180 billion years, right? Our next scenario technically could happen at any moment. It's part of why it's my favorite. Okay, so vacuum decay. Vacuum decay is an idea that's been around for quite a while, but it got a lot more attention in 2012 because of this. So this is an event display from the Large Hadron Collider at CERN in Geneva. The Large Hadron Collider is a machine that smashes protons together and looks at what comes out. What it's really doing is trying to recreate the conditions of the very early universe, to create that hot, dense state, to see how the laws of physics were different in the early universe than they are today. And one of the things that it does is it tries to figure out all of the particles that exist in the universe, all of the interactions between those particles, what their properties are, all of that. And through the Large Hadron Collider and other measurements, we've been able to put together the standard model of particle physics and understand the components of standard model of particle physics. So this is a chart of the standard model of particle physics before 2012. This is a chart after 2012. So in 2012, the Higgs boson was discovered at the Large Hadron Collider. The Higgs boson is a particle that is associated with what's called the Higgs field, which is kind of an energy field that's throughout all of space. And this energy field has to do with how particles got mass in the early universe. It has to do with the properties of the particles, and I'll tell you a little bit more about that in a few minutes. But let me first go through this chart and tell you what each of these particles are, because the standard model of particle physics is a pretty important piece of our understanding of the universe. This is every particle that's ever been detected or seen or inferred in an experiment. Okay, so the sort of blue-purple side, those are the quarks. So the quarks they're these subatomic particles. They're kind of the things that make up the proton and the neutron. They come in 6 different flavors. They're called flavors. The flavors are up and down and charm and strange and top and bottom. They were named in like the 60s and 70s. People were doing weird things at that time. But if you look at like what the proton and the neutron are made of, they're made mostly of quarks. It's a little more complicated than that when you get into it, which is deeply frustrating. But anyway, usually people will say that the proton is 2 up quarks and a down quark, and the neutron is 2 down quarks and an up quark. The green ones here, these are the leptons. So there's the neutrinos. These are little ghostly particles that kind of move through us that come from the sun. And then the electron and the muon and tau particle. The electron is the particle that goes around the nucleus. So there's the protons and neutrons in the center, and the electron is kind of orbiting around, except when you get more into quantum physics, you find out it's not really orbiting so much as it's kind of a cloud of electronness kind of around the atom. That gets very complicated as well. And then the muon and the tau particle are kind of the cousins of the electron. And then there's, in the red there, those are the gauge bosons. Those are particles that have to do with the forces of nature. So there's the photon. The photon is a particle of light. It's why you can see stuff. It's how light moves around. It's also responsible for the electromagnetic force. So it's electromagnetic waves, electromagnetic forces, all of that. And then there's the gluon. The gluon is the mediator of the strong nuclear force. That's what holds the protons and neutrons together inside the nucleus. And then there's the Z and the W bosons. These are particles that have to do with things like radioactive decay. So they have to do with how particles can change from one kind of particle to another. Now, I mentioned before that the Higgs field, this kind of field that pervades all of space, it has to do with how particle physics works in our universe. So you just have to imagine there's like this energy field everywhere, and the different particles interact with the Higgs field in different ways, and in the very, very early universe, the Higgs field was different, okay? This energy field everywhere, it's called a scalar field, which means that it has a particular value, like a number associated with it everywhere. And the number that's associated with the Higgs field now is different than the number that was associated with the Higgs field in the very, very early universe. And that number determines how all of these particles work, basically. It determines the state of particle physics in the universe. When the Higgs field changed from the value it had in the very early universe to the value it has now, it set up the conditions for the standard model of particle physics to exist. Before the Higgs field changed, these particles were not the particles of nature. We didn't have particles that had mass. You didn't have atoms. You couldn't have nuclei. Then the Higgs field changed, something happened, the Higgs field changed, and we got the standard model. Now, there's a question of whether the Higgs field will always stay the same as it is now, because we know it did change in the past. So there's a question of, is the Higgs field stable now? And this is a plot from a paper from 2012, shortly after the Higgs boson was discovered, and we started to learn more about the Higgs field. It turns out that by looking at the mass of the Higgs boson, the particle that's associated with the Higgs field, and the top quark, by looking at those two parameters, we can learn something about whether the Higgs field we have today is stable or not. Okay? So for different combinations of these two masses, we get the universe being stable or unstable, or having some kind of problem where you can't get the equations to work out. So, for example, if the mass of the Higgs boson is 100 GeV, so GeV is it's a measure of energy, but we use it for mass, it's giga-electron volts. If the Higgs mass was 100 and the top mass was 50, we'd be in a nice, stable region of this plot, right? We'd say that the Higgs field is never going to change again. It's totally stable. We're good forever, okay? If the Higgs mass is 100 and the top mass is 200, then the universe is already unstable. It already collapsed. Everything already became destroyed, right? If the Higgs mass is 200 and the top mass is 50, then we live in some part of the parameter space that the equations don't make sense anymore. So once we've discovered the Higgs boson at the Large Hadron Collider, we can measure that number along the bottom, and we can draw a point on this graph for where we live based on already knowing the mass of the top quark. And it's there. So that's the region of meta-stability, which means it's stable for now. It's like, so meta-stability is like, if I take this water bottle and I put it right at the edge of this table, so there's some number associated with the height of that water bottle, right? It's maybe, I don't know, a meter, something like that. There's also a number for the height that the water bottle would much rather be at, and that's 0, right? And that means that if the water bottle is okay, but if something were to just kind of tap it a little bit, it would end up where it would rather be, right? So in this case, there's a gravitational potential Gravity is telling the water bottle it would rather be down there. It's perfectly fine for it to be up here, as long as nothing moves, nothing touches it, right? It's okay there for now. That's metastable, okay? And we think maybe the universe, the Higgs field is kind of like that. So here's a plot from a paper from 1980 talking about the metastability of the Higgs boson, or the Higgs field, back before we measured anything about the Higgs boson. And they were exploring the possibilities, right? And so these two little valleys represent different parts of the potential for the Higgs field. The potential is not a gravitational potential like it is for this water bottle. It's a different kind of thing, but it determines where the Higgs field would like to be, what number the Higgs field would like to have. And if our universe is in that little valley, then that means that our universe, the Higgs field in our universe has a number that is not the number it would prefer to have. So that one's the higher potential, the other one is the lower potential well, and it would kind of rather be at the other one. And if this is the case, if this is how our universe is set up, then the part of the sort of setup that we have is called a false vacuum, where by vacuum we just mean like the state of the universe. The vacuum state is how we talk about like how the universe is set up. We live in a false vacuum, and that over there is the true vacuum, the preferred state of the universe. If that's the case, then we have a bit of a problem, because that means that in principle, something could disturb the Higgs field, just like I could disturb this water bottle. Something could disturb the Higgs field enough that it kind of jumps over that hump and ends up in the true vacuum. And that would be bad, because the true vacuum is a different setup for the universe. It's a different setup for particle physics. It's a kind of particle physics where we don't have atoms, we don't have particles that have mass, where we have just a totally different mix of how physics works in the universe. And we don't want that to happen, because that would be really bad for us, because we depend on the existence of things like atoms and chemicals and all of that good stuff, right? We want our quarks to have mass. Like, there are various things that we would like in our universe that do not work out in a true vacuum. So there's good news and bad news. The good news is that we don't know of any way for the universe to get the ball over that hill. So we don't know of any way to make the false vacuum transition to the true vacuum by giving it the kind of energy that it would need to go over. Kind of like if I were an ant trying to knock this water bottle over, I would not be able to do it. But the bad news, our universe is fundamentally ruled by quantum mechanics. And you may have, at some point in school, learned a little bit about quantum mechanics and learned about something called quantum tunneling. So quantum tunneling is this idea that if you put a particle on one side of a wall and you wait long enough, eventually it'll just show up on the other side. It doesn't have to go around, it doesn't have to break through it. It'll just happen to be on the other side. That's quantum tunneling. And in principle, if I left this water bottle here long enough, it could quantum tunnel through the table and end up on the floor. It would take a ridiculously long amount of time, but in principle that could happen, because particles can do that in quantum mechanics. They can just quantum tunnel. And unfortunately, that also applies to the Higgs field. So the Higgs field could be perfectly happy in a false vacuum, and one day it could just tunnel to the true vacuum state. And because the Higgs field is everywhere, every point in space that could happen, technically at any moment, because we can't predict quantum tunneling. We can talk about rates. We can say if you put an electron on this side of the wall, how long on average you'd have to wait to find it on the other side, but you can't say exactly when that transition is going to occur. So if that happened somewhere in the universe, if the Higgs field tunneled to the true vacuum somewhere in the universe, here's what it would look like. So you would have a bubble that would form at the point where that transition occurred, where that quantum tunneling event happened. And that bubble would have a sort of bubble wall around it, a sort of high energy sort of surface. And that bubble wall, as it moves through space, it would kind of incinerate everything it touches. And the interior of the bubble would be that true vacuum state with the different physics. And that bubble would be would be expanding at about the speed of light, which means that if you're standing nearby when it happens, there's no way you're going to see it coming. Because by the time the light from it gets to you, it is already here. It's good news. It means you can't feel it either because it goes too fast. It's fairly humane. But once that bubble hits you, you're incinerated by the bubble wall, and then you're inside the bubble, you're in the true vacuum, your atoms don't hold together anymore, chemistry doesn't work, you are disintegrated at the subatomic level. Now, that drawing I showed you before was from the paper by Coleman and DeLucia from 1980 when they were going through these possibilities. And when they calculated this, they were working through the possibility of this vacuum decay, and they were working out like exactly what would happen afterward. And they calculated that inside that bubble of true vacuum space, also it's gravitationally unstable, which means that after you get incinerated and after your atoms fall apart, then you also collapse into a black hole. And they worked through the calculation, and then they wrote down a little paragraph of reflection about it. And I just want to share that with you because it's one of my favorite pieces of physics poetry that I've ever read. Okay, so they just did this calculation. Inside the bubble, everything collapses to a black hole, and they say, this is disheartening. The possibility that we're living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. So, I don't want you to worry about vacuum decay. There are a number of reasons I don't want you to worry about vacuum decay. One of them is that, we can calculate the expected tunneling time, and it's much longer than the age of the universe. The numbers we see are something like 10 to the power of 100 or 10 to the power of 500 years, really far into the future, even if it were going to happen. Also, you wouldn't feel it. You wouldn't notice. It happens so fast. You wouldn't even have time to process it going on. You're not going to miss out on it. There's no tragic aftermath. Everything is just over. In some ways gentle, very clean. But also, if we look at this is a pie chart of what the universe is made of as far as we understand it. Dark energy is most of it, as I mentioned before. The next biggest chunk is called dark matter. This is some kind of invisible stuff that makes up most of the matter in the universe. It's most of what I work on in my research. It's something that we can't see, we don't know what it is, but we're pretty sure it's out there and it's most of the matter in the universe. And then there's this little 5% slice here, 4.9%, that I've labeled atoms. And that contains the entire standard model of particle physics. So I told you the standard model of particle physics is everything we've ever seen or detected or really understand in any kind of laboratory experiment. Everything we know is out there and we know how to talk about it. And that means, and the idea that vacuum decay could happen, the idea that we're in a false vacuum, depends entirely on trusting the standard model of particle physics completely and saying there's nothing else is going to happen. The standard model of particle physics tells us everything we need to know about the universe. And if you look at that graph, you can tell that there's other stuff there, right? There is a lot that we don't understand about the universe. And in order to explain dark matter, in order to explain dark energy, we're going to have to expand our understanding of particle physics beyond the standard model. We don't know what that's going to look like yet. We don't know how that will change our picture of particles, of interactions, of the state of the universe, but we do know that we don't have the whole picture now. And so, as much as it's really interesting to go into all these possibilities for the future of the cosmos, we're still in a place where most of the cosmos is a mystery, and there's so much more to understand. And maybe when we really understand all of those things, we'll find something completely different, completely unexpected future for our universe. So I think I'll just end it there. Thank you very much, and I can take some questions.